Let's take a look at some other examples of evaluating limits as x approaches infinity or negative infinity. So in these examples here, you're going to see that they include square root x or square roots of some sorts. So let's take a look. For my first example, for question A, I've got the limit as x approaches infinity for x plus square root x squared plus 1 divided by 3x plus 2. So if I take a look at this, I know that the first thing that comes to mind for many of you is going to be, I need to rationalize. But when you're dealing with limits at infinity, you don't need to rationalize, okay? But we're going to approach it the same way. We want to take out or factor out the highest exponent of x. Now, in this particular case, I'm just going to rewrite my question first. We notice that, okay, my numerator, I've got x. But technically, if I look at my square root, if I square root x squared, I'm still going to get x. So what we're going to do is we're going to pull out the x squared from the square root, and we're going to use the fact that we can split up radicals to help us out. So I'm going to still have x here plus, and then I'm going to do the following. I'm going to factor out the square root of x squared, and that's going to leave me with 1 plus 1 over x squared. Remember, if you have two things being multiplied underneath a radical, you can split it up as two radicals. And then all over, I'm going to do the same thing with the denominator. I notice that the highest exponent of x there is just 1, so I'm going to factor out x then. So if I factor out x, I'm going to be left with 3 plus 2 over x. Now, before I do anything, I'm just going to simplify everything first, just to make it look a little bit cleaner for us. So I've got x. Now in this case, since I'm going to positive infinity, I can leave the square root of x squared as just positive x. There's going to be a case where we don't do that, which I'm going to get to later on. And then I have the x, and then 3 plus 2 over x. Now, right now, in my numerator, it's hard for me to cancel things out with the denominator. So what I'm going to do is I'm going to factor out the x from everything in the numerator now. So if I do that, I'm going to be left with x and then 1 plus the square root of 1 plus 1 over x squared, and then all over x times 3 plus 2 over x. Now, at this particular stage, just like how we were doing before, anything that's in a fraction form, like 1 over x, or 2 over x, or 1 over x squared, we know that that automatically is going to head towards 0, since in our case, any 1 over a really, really large number is going to head to 0. So this is going to head to 0 for us. This is also going to head to 0. Which means, technically speaking, I'm left with the following then. The limit as x approaches infinity, and I realize I can also cancel out the x's. I forgot about that. So then I'm really left with 1 plus the square root of 1 over 3. And if I simplify that, technically my limit is then 2 over 3. So in this particular case, the limit as x approaches infinity for x plus the square root of x squared plus 1 all over 3x plus 2 equals to 2 over 3. Let's take a look at example B, which is the same concept here. Okay, so I've got the limit as x approaches infinity for 2x plus square root of x squared plus x, and then all divided by x plus 3. So the same thing, I'm just going to rewrite my limit out first. And again, I'm going to take a look. I want to look for the highest exponent of x in my numerator and my denominator. Now, in my numerator, I notice that I have 2x, but at the same time, I notice I have x squared underneath the radical. So I'm going to take out the x squared from underneath the radical, and I'm going to rewrite it this way now. So I'm going to have 2x plus the square root of x squared times, and then this is going to leave me with 1 plus 1 over x. And then all over. In my denominator, the highest exponent for x is just x. So I'm going to do x, and then I'm going to be left with 1 plus 3 over x. Alrighties. So again, I'm just going to simplify some things. I'm going to have the limit as x approaches infinity. Then I'm going to have 2x plus the square root of x squared. Because I'm dealing with positive infinity, I'm going to leave it as just plain old x. And then I'm going to do square root of 1 plus 1 over x all over x times 1 plus 3 over x. So now I'm going to go about and I'm going to start canceling things out when I need to. So I'm going to do the limit as x approaches infinity. And I'm just going to rewrite so that I can end up canceling everything out that I need to. Oops, I forgot to factor out the x from my numerator, so it makes it easier for us to cancel. So I'm just going to factor out my x, and I'm left with 2 plus the square root of 1 plus 1 over x. And then in my denominator, I'm just going to finish writing out that. So right away, I know that my x's cancel, as well as I noticed that if I had like a number over x or a number over x squared, those automatically go to 0 now. So what I'm finally left with is the following. The limit as x approaches infinity, I have 2 plus the square root of 1 all over 1. And if I simplify that, that gives me 3. And there we go. So the limit as x approaches infinity for 2x plus the square root of x squared plus x over x plus 3 is simply 3. Let's take a look at our bottom two examples now. Question C and question D. So taking a look at question C, I've got the limit as x approaches infinity for square root 2x squared plus 1 over 3x minus 5. The same approach that we're taking. We're going to rewrite our limit first. I'm going to have the limit as x approaches infinity, and then I'm going to take a look at my numerator. I want to factor out the highest exponent of x. In this case, what I'm going to do is I'm going to take out the x squared from underneath the radical. So I'm going to break it up how I've been doing it so far. So I'm going to do the square root of x squared and then times 2 plus 1 over x squared. All over. In my denominator, I'm factoring out x, and I'm going to be left with 3 minus 5 over x. Again, I'm just going to simplify first before we think about canceling anything. So because I'm dealing with x approaching positive infinity, the square root of x squared is just going to be positive x for us in this particular case. And then I've got 2 plus 1 over x squared all over x, and then 3 minus 5 over x. Right away, I notice that I can cancel x and x out. And then as well as I notice that there are some things with fractions. So these will go to 0 for me now. So at the end of the day, if I rewrite this, the limit as x approaches positive infinity, I'm going to get root 2 over 3, and then that just stays as root 2 over 3. And there we go. So in this particular question, the limit as x approaches infinity for root 2x squared plus 1 over 3x minus 5 is just root 2 over 3. Now, taking a look at D, you're going to be like, oh, miss, it's the same question. And then you're like, but wait, this one here, x is approaching negative infinity. So how is that going to change things for us? So I'm going to start off my question very much the same way that I did for question C. So it's still going to look like the following. The limit as x approaches negative infinity, I'm still taking out square root of x squared, then times 2 plus 1 over x squared, and then all over x times 3 minus 5 over x. So just the same thing that I was doing for question C. But now I would like to talk about what happens in this particular scenario since I'm going to negative infinity. So in this particular case, this is where we have to be more observant now about the square root of x squared. In examples A, B, and C, we always just said that the square root of x squared was x, but that's because it was going to positive infinity. If you were to graph the square root of x squared, it actually looks like the absolute value function, which is what I'm going to draw for you here. It looks like the absolute value function. So that's why when we were dealing with when x is approaching positive infinity, in all those previous questions, when x was approaching positive infinity, we were allowed to say that x squared was just equal to x because it was on the right-hand side of x equals to 0. But now, since we're talking about x approaching negative infinity, we're looking at the left-hand side of x equals to 0 now on this graph, which means the square root of x squared, we will have to take negative x instead, okay? Because we're looking at this portion. We're looking at this portion of the graph here. That's why we're taking negative x. So in this particular case, you have to be very, very careful when you're dealing with square rooting something, when you're dealing with limits at infinity. So this is now going to change for us. So if I simplify this, it now becomes the limit as x approaches negative infinity. Rather than positive x now, you have negative x. And then square root 2 plus 1 over x squared, all over x, and then 3 minus 5 over x. Now the same thing holds here. Technically speaking, if you have like negative infinity, that's a number like negative 1,000, negative 1,000,000. 1 over the square root, the square of negative 1,000,000, that's going to head to 0. Same thing with 5 over x. You put 5 over a really, really, quote unquote, what we call small for negative sake. Let's say 5 over negative 1,000,000. That's still going to head over to 0. And then my x's can cancel as well. So I'm really left with the limit as x approaches negative infinity of negative root 2 over 3. And then that just simplifies to just negative root 2 over 3. So the limit as x approaches negative infinity for square root 2x squared plus 1 over 3x minus 5 gives us negative square root 2 over 3. So whenever you're dealing with radicals, with x approaching positive or negative infinity, you have to be mindful. If it's going to positive infinity, it's okay. But when it's going to negative infinity, that's where you have to make that change. It's no longer just x. It's actually going to equal to negative x instead. All right, on to our last example, which is example E. So let's take a look at that. So for example E, this one here doesn't have any radicals, so we don't have to worry about what we were doing in example A to D. It does ask, what's the limit as x approaches plus or minus infinity of 2x plus 1 times x plus 2 all squared, all over 5x squared plus 2x. Now, sometimes mathematicians get a little bit lazy, and rather than writing two separate limits, we combine them together. That's why you see x approaching positive and negative infinity all in one shot. In that case, you are going to have to solve two different limits for me. So just keep that in mind. But I know that in many cases, many of you are going to try to expand the numerator. Don't do that. All you have to be concerned about in this particular case, if you're dealing with a rational function like this, don't expand. I just want you to figure out what's the leading term. In other words, the term that will have the highest exponent of x. So if I take a look at 2x plus 1 and then x plus 2 squared, if I was to quote unquote want to expand this, I would get 2x plus 1 times x plus 2 times x plus 2. Technically, when you multiply all of the x's in each of your factors, that's going to give you your leading term there, which is going to be 2x cubed. I don't care what happens after that. That's why you see me do ... Has no concern for me. Okay. And now let's take this and use this to help us. So we're going to actually do two different limits. So I'm going to start off with the limit as x approaches negative infinity. Rather than using that factored form, I'm going to use that makeshift expanded form that I've got there, which is the 2x cubed plus everything else that's going to happen at the end, and then 5x squared plus 2x. Now, here's the thing. Even if you were to expand, you know that by the time you factor out that x cubed from the numerator, everything else is going to end up 0 at the back anyways. So technically, you've got the limit as x approaches negative infinity. If I factored out the x cubed, I would be left with 2 plus all of this stuff at the back would have ended up in a fraction, right? It would have been like something over x squared, something over x, something over x cubed. In my denominator, if I factor out x squared, because that's the highest exponent of x down there, I would be left with 5 plus 2 over x. I already know that this is already going to 0. This is also going to 0. And then I end up canceling out x squared and the x cubed. And I end up with the limit as x approaches negative infinity for 2x over 5, right? Because I still have those numbers 2 and 5 there. Now think about this logically. If I was to plug in a super small number, say negative 1,000, negative 1,000,000 in for x, the limit here would essentially head to negative infinity. Okay? So if you did 2 over 5 times negative infinity, you're still going to get negative infinity. So that's the limit as x approaches negative infinity for my function. And now let's take a look at what happens when we're going to positive infinity. So if I take a look at the limit as x approaches positive infinity, again, I'm going to use that makeshift expanding that we did. And then I'm going to divide it by 5x squared plus 2x. I'm going to do the same thing. I'm going to factor out that highest exponent or power of x. So in this case, I'm going to get the limit as x approaches infinity, and then I'm going to do x cubed at the top. That leaves me with 2 plus all this stuff that's going to happen at the back. And then I'm going to factor out x squared, and that's going to leave me with 5 plus 2 over x. Again, we already know everything at the back here is automatically going to go to 0. 2 over x is also going to go to 0. And then x cubed and x squared, they reduce. And then I will be left with the limit as x approaches infinity for 2x over 5. Again, I want you to think about this. If you plugged in a super large number, say 1,000,000, 1,billion, into x and you did 2 over 5 times that big number, you're still going to get a positive big number. So in this case, it goes to positive infinity. So the limit as x approaches infinity for our function is positive infinity now. So we've gone through evaluating our limits when x approaches positive or negative infinity. This concept of taking out the highest power of x is only applicable when you are solving limits at infinity. Do not use it anywhere else. If you see that x is approaching plus or minus infinity, you can factor out the highest power of x. If it's going towards a number, say an integer, a fraction, you cannot use this method. If you do, you will not get something that makes sense. It won't work. Okay? So please, please, please make sure that you only use this method of factoring out the highest power for limits at infinity.